Hello friends, welcome back to my YouTube channel EDUFYI. Today's topic is fields, is the continuation of rings and fields in the BSc final year chapter. Before going into the topic, if you find this video interesting, make sure you give the thumbs up and share the video, and also make sure you subscribe to us so it boosts us the confidence to make new videos, and ring the bell icon for further notification. I have already done a video on rings, so you can check it out. The link will be down in the description. Now we'll be moving on to the fields. What is a field? Rings and field are pretty much simple. I will be also doing a new video about the difference between the rings and fields. You can also check it out. Let R be a non-empty set and plus and dot be binary operations. It is same as rings. The definition is same as rings. Let R be a non-empty set and plus and dot be binary operations on set R, which is denoted as R comma plus comma dot, is a field. It is same definition as rings. Let R be a non-empty set plus and dot be binary operation on set R, that is R comma plus comma dot is a field if it satisfies. Now is the difference between the fields and the rings comes. If it satisfy, the first one is R comma plus is additive abelian group. This is same as ring. Even in ring you prove that R comma plus is an additive abelian group, but the second one is different. In ring you prove that R comma dot is a semi group, but here we are proving R comma dot is a multiplicative abelian group. In the rings you are proving that R comma dot is a multiplicative semi group, but we are in fields we are proving that R comma dot is a multiplicative abelian group. The third one is same as ring, that is R is distributive law. You know what is abelian group? We know that abelian group it must satisfy the closure law, associative law, identity law, inverse law, and commutative law. Same goes with the multiplicative abelian group. It must satisfy closure law, associative law, commutative law, identity, and inverse law. And distributive law, also we know that R is a distributive law for all A, comma B, comma C belongings to R. The left law says that A plus B dot C is equals to A dot C plus B dot C, and the right law states that A dot B plus C is equals to A dot B plus B dot C. If this is being proved, then R comma plus comma dot can be said as field. If you find rings and fields both are same and what is the difference, you need to know. I'll be putting another video known as the difference between rings and fields. You can check that video. So now we have found out what is field. It's a non-empty set where plus and dot are binary operations on set R, that is R comma dot plus comma dot is a field if it satisfies R as a additive abelian group and R as a multiplicative abelian group and R as a distributive law. Let us consider an important problem. We'll take an important problem itself because you have solved the ring problem, so you know what is abelian group, what is how to prove it is an abelian group. So we are going to the one of the important problem here. The problem is state that the set of all complex number is a field with usual addition and multiplication. So they are asking to prove the complex set of all complex number as a field. Now what is the set of all complex number? Let us define what is set of all complex number. It can be written as C is the symbol of complex number. Complex number can be defined as x plus iy, where x and y belongs to real numbers and I is equals to root of minus 1. This is the defining how the complex number is, that is C is equals to x plus iy, where x and y belongs to real numbers and I is equals to root of minus 1. Now let us take let us consider A is equals to x1 plus I y1 and B is equals to x2 plus I y2 and C is equals to x3 plus I y3 for all A comma B comma C belongs to real numbers, x1 y1 x2 y2 x3 y3 belongs to real numbers. We must prove that R is a, the first case is, first we must prove that R is a additive abelian group. So now first we have to prove that R is an additive abelian group. Then we must prove that R is a multiplicative abelian group. Finally, we must prove that R is a distributive group. If we prove this, then it is called as a field. We can prove it as abelian group because you know how the group theory, so you can prove it as an abelian group. You can also prove it as a multiplicative abelian group. You can also prove it as a distributive group. Now I'll be doing this problem with respect to the ring and then proving it as a field. I'll tell you how. You're simply proving it R is an additive abelian group. Yeah, you proved that R is an abelian additive abelian group by proving closure law, associative law, identity, inverse, and commutative. You proved it that R is an additive abelian group. You also proved the third one, that is R is distributive. You prove the second one as R is a semi-group, that is multiplicative semi-group. You prove that R is an additive abelian group, R is a distributive law, and R is a multiplicative semi-group. So what does it becomes? Then it becomes R is a R comma plus comma dot is a ring. It is now a ring because you proved it as semi-ring. You didn't prove it as abelian group. So you proved it as a ring. But in concept of ring, it is said that if a ring is said to be if a ring is said to be a commutative ring, if this ring is a commutative ring and also a division ring, if this ring is a commutative ring and also a division ring, then this ring is called to be as a field. So let us prove it as a commutative ring first. So to prove commutative ring, we know that for all A comma B belongings to R, commutative law states that A dot B is equals to B dot A. So A is what? x1 plus iy1 dot multiplied with x2 plus iy2 is equals to x2 plus, we must prove that it is equal to x2 plus iy2 multiplied with x1 plus iy1. So multiply with this one, x1 x2 plus x1 iy2 plus x2 iy1 plus iy1 iy2. So moving x1 on all sides, you get x2 on the one side and x1 on the other side, you get x2 plus iy2 plus into x1 plus iy1. So you proved it as commutative law. So it is ring. This ring is called to be as a commutative ring. Now we must prove it as a division ring to prove it as a field. Now to prove it as a division ring, the definition of the division ring is simple. Every non-zero element of a set must have its own inverse. Then it is proved to be as division ring. Every non-zero element must have an inverse to prove it to be it as a division ring. So let us consider A, that is x1 plus iy1. The inverse of A is 1 by A. Inverse of A is equals to 1 by A, which is equals to 1 by x1 plus I y1. Can we multiply it with x1 minus I y1 by x1 minus I y1? So this cancels, it becomes same as 1. So if you multiply this x1 minus I y1 by a plus b into a minus b is x1 square minus I y1 whole square. We will split the denominator. So x1 by x1 square minus I y1 whole square minus of I y1 by x1 square minus I y1 whole square. We can write this same as x1 by x1 square minus I y1 whole square plus minus we take it inside I y1 by x1 square minus I y1 whole square. This is same as the what we have considered over here, that is x1 plus I y1. So this is as x plus I y1. So this proves that this also belongs to the complex number. So this proves that the ring is a division ring. So we proved it as a commutative ring and also a division ring. So the ring is a field, because field, the definition of a field also says that if a ring is a commutative ring and a division ring, then it is a field. So this proves that every set of complex number is a field. Thank you.